Hi everyone, this is Yunjie from National Taiwan University of Science and Technology, and my advisor is Professor Xiaoyun Feng. Today, I'm here to introduce my paper, COALA, Concurrently Assigning Wire Segments to Layers for 2D Global Routing. In this work, we consider to assign all wire segments of 2D global routing paths to layers concurrently and get a solution efficiently. I am Yunjie Zhang from National Taiwan University of Science and Technology. I specialize in electronic design automation, physical design, and design for manufacturing. This is my outline. I will first introduce the conventional sequential layer assignment approach and give the idea of our concurrent layer assignment method. Then, I will present our COALA framework and give a simple instance. In the framework, two useful maps are proposed that can help us to avoid overflow during concurrent layer assignment. After that, I will detail the algorithm of segment assignment and three-dimensional rerouting. And finally, I will show the experimental result and conclusion. Let's get started from the introduction. In conventional layer assignment process, the first step is to determine the assignment order of all nets. Then let's solve the problem with dynamic programming net by net to minimize some cost functions such as number of vias. Although the optimal solution can be found for each net sequentially, the conventional way may cause three issues. The first issue, it is hard to get the optimal assignment ordering in complex designs. Even worse, an optimal layer assignment solution may not be found by using any segment ordering. The second issue, the conventional way is harmful to nets which ranking behind. Although the solution is built by optimal solutions, the nets which ranking behind may not have enough routing resources, so that those nets will must suffer from overflows. Here is a simple example. In Figure 1, it presents a feasible two-dimensional routing pattern. If the routing order is blue net before red net, the red net will be blocked. Because the blue net chooses the shortest path, which is the optimal solution at the moment. No matter how the red net is assigned, its optimal solution will end up with at least one overflow. The third issue, to get a better solution, it is common to use some post-refinement process after the dynamic programming-based layer assignment, such as rip-up and rerouting. However, the refinement problem is another difficult problem, and rip-up and rerouting may not be effective because routing resources have been scattered. Hence, this paper proposes a method that can consider all nets concurrently, make full use of routing resources, and make every single net can get the routing resource fairly, and thus reduce overflows. Different from the conventional approach performing layer assignment net by net, our algorithm do it layer by layer. The figure below shows how the concurrent layer assignment works. In all the examples and benchmark we use in the work, Method 1 is not used for layer assignment. In Figure A, we concurrently assign all the vias from Method 1 to Method 2 for the pins on Method 1. With this known via demands, we can do segment assignment by avoiding overflows. Therefore, we will not assign the blue segment on Method 2. Instead, we assign the two red segments on Method 2. In Figure B, we also concurrently assign the necessary vias from Method 2 to Method 3, and assign the horizontal red segment on Method 3, and so on. When it gets to the top layer, we finish our layer assignment. The details of our proposed COALA are detailed in the following. This figure shows our concurrent layer assignment framework. First, we parse the two-dimensional global routing pattern. Then, the layer assignment process is done from the bottom layer to the top layer. In every layer, we first initialize the pins and assign the necessary vias on current layer. Based on this known vias demand, we carry on two types of segment assignment. The first type is complete segment assignment. In this step, we try to assign the segments on the net which are almost complete. This is because if more nets can be completed in lower layers, fewer vias are necessary to be assigned to connected incomplete nets to upper layers. This can prevent the large amount of vias from occupying the routing resources. The second type is fragmented segment assignment. In this step, we make full use of remaining resources by cutting wire segment to appropriate fulfill the remaining resource. After the process is iteratively performed to the top layer, for those unassigned segments, we collect them and do three-dimensional rerouting. At last, we get our layer assignment result. Here is a trivial instance. The figures below demonstrate process of via assignment and maintaining candidate segment and candidate endpoint. The two-dimensional global routing pattern are given in Figure A and Figure B, which denotes endpoints and wire segments, where P1 is a metal 2 pin and P4, 5, and 6 are metal 1 pins. Starting from metal 1, as illustrated in Figure C, the pin P4, 5, and 6 are added to candidate endpoints, and their connected segment S3 and 4 are added to candidate segments. Since no wire segment can be assigned to metal 1, moving to metal 2, the pin on metal 2, P1, is added to candidate endpoints, and its connected wire segment, S1, is added to candidate segment, as shown in Figure D. Before tackling the wire segments on metal 2, we assign vias connecting metal 1 and metal 2 and deduct the demands in candidate endpoints from the tile capacity on metal 2. Note that in the rightmost column, due to the capacity deduction by vias, S4 cannot be directly assigned to metal 2. As a result, only S1 and 3 are assigned to metal 2, as shown in Figure E. After assigning S1 and 3, the two segments are removed from candidate segment, and P1 and 4 are removed from candidate endpoints. In addition, P2 and 3 are added to candidate endpoints, and S2 also becomes a candidate wire segment. Moving to metal 3, vias are first assigned and illustrated in Figure F, and S2 is assigned to metal 3, as shown in Figure G. Since all the connected segments of the two endpoints of S2 has been assigned on layers, P2 and 3 are removed from candidate endpoints. Finally, the two vias at P5 and 6 in candidate endpoints and the remaining segment S4 in candidate segment are assigned to metal 4, as respectively shown in Figure H and I. In our algorithm, we use the capacity map and an innovative demand prediction map to guide the layer assignment process and avoid overflow on the top layer. Since in addition to wire demand, via demand in global routing is also critical for routability, which has been addressed in many previous work. We model capacity and demand on the vertex of global routing graph. The reason is that each capacity cannot count via demands. Therefore, the figure below shows how we convert each capacity into vertex capacity. In Figure A, we assume that there is only one track path through every G cell, except for metal 1. In metal 1, there are a lot of access pinpoints, so we choose not to assign any segments. Figure B shows that the edge capacity is 1, which represents only one segment can pass an edge. And so on, the capacity on metal 1 will be 0. In Figure C, we convert edge capacity to vertex capacity by adding the two adjacent edge capacity to the connected vertex. Hence, the final vertex capacity is 1, 2, 2, 1 in each row and column. Based on the capacity map, we propose an innovative demand prediction map. This map can guide us to find segments that should have higher priority to be assigned during the following process, and this demand prediction map can effectively reduce overflows. The idea is to infer the fewest wire segments that are required to be assigned to current layer. Here's an example. Figure A is a capacity map of column of global tiles, which we mentioned in the previous page. Suppose we need to assign 2 segments to column, as shown in Figure B. Similar to the way we use to calculate the capacity of each tile, we assume the demand value of crossing wire is 2 and that the line end is 1. As shown in Figure B, the total demand of the 2 segments is 1331. The Figure C, we allocate the demand values from the top layer to the bottom layers. The maximum capacity of metal 4 is 1221, and the routing demands are all greater or equal to maximum capacity. Therefore, the demand prediction map of metal 4 is 1221. After assigning the demand values to metal 4, the remaining unassigned demand values become 0110. Since the unassigned demand values are fewer than the capacity values on metal 2, we directly assign those values on metal 2 during our layer assignment process, which is from the bottom layer to the top layer. The number in the demand prediction map indicates the number of segments that should be assigned to the tile on the current layer. We must meet the map, otherwise, overflow will must occur on the top layer. In this section, I will introduce 2 types of segment assignment: complete segment assignment and fragmented segment assignment. For each layer, we first assign segments by using complete segment assignment. In this step, to minimize the number of vias and maximize the utilization of routing resource, we first assign complete segments as many as possible. The assignment follows 3 ordering criteria below. First, the residual parts of fragmented segment have the highest priority to assign it. It is because if residual part of fragmented segment is not assigned, other segments of the same net cannot become candidate segments. The second criteria is degree of the net completeness. If most segments of net can be assigned on lower layers, the remaining segments of net should have higher priority to be assigned. It is because if all the segments of net have been assigned on layers, the net will no longer cause any via demands. The third criteria is segment length. If 2 segments have the same net completeness, we prefer to assign the shorter segment before the longer segment. Practically, it can result in fewer vias and thus less overflow. After no complete segment can be assigned, we update the demand prediction map and capacity map. Figure A shows the initial prediction map and the initial capacity map. Suppose we assign 3 complete segments on metal 2 and show in Figure B. The complete segment demand is 112431. And demand values are subtracted from the capacities and prediction demands on metal 2, and thus the remaining capacity are 132011, and the predicted demand maps become 01 -1 -201. The remaining capacities means that there are still routing resources, and the positive demand values indicate that if no other segments are going to be assigned on metal 2, overflow will be caused on the top layer. Therefore, the remaining resource can and should be further used by fragmented segments. In fragmented segment assignment, we make full use of remaining resources. In Figure A, we color the tiles with remaining capacity in green and the tiles with no capacity left in red. In addition, the tiles with positive demand prediction values are colored in blue in Figure B. According to the three-tile statuses, fragment segment assigned to current layer cannot overlap red tiles. In addition, it is more desirable to assign fragment segment overlapping with blue tiles to avoid overflows on the top layer. To achieve this goal, we first divide the tiles array into subtile array by red tiles. Then we focus on the single subtile array at a time. The candidate segment can be fragmented and assigned to the subtile array if the following two conditions are satisfied. The first condition is that its connected via to the lower layer must lie on the subtile array. In Figure C, the first segment is not candidate segment because the connected via lies on the different subtile array. The second condition is that its fragment segment has to overlap the subtile array with more than one tile. In Figure C, the second segment is also not a candidate segment because there is no overlaps. Only the third segment in Figure C matches the two conditions. Therefore, we cut the segment into two parts. The left part segment can be assigned to the current layer, and the fragmented right part of the segment will become candidate segments. Suppose we assign one fragmented segment to this column, whose demand is 121000. Then the demand values becomes those shown in Figure A. Suppose no fragmented segment can be assigned to the current layer anymore. The prediction map will be updated. We use the resulting demand values on metal 2 to update the demand values on metal 4 by simple addition. The original metal 42442, adding the value is in metal 2, -1, -1, -2, -2, 0, 1. The new prediction value of metal 4 will be 132243. It is worth to mention that the rightmost value 3 are larger than the original value 2. It means that overflow must occur in the tile on the top layer. The last step of our framework is three-dimensional routing. The reason that overflow may be generated after layer assignment is because of the gap between two-dimensional global routing and three-dimensional layer assignment result. In two-dimensional routing, every band of each net may cause unpredictable via demand. In other words, even if there is no overflow in 2D global routing result, overflows can be caused after the 2D routing patterns are converted to 3D routing pattern. The gap may cause lots of unpredictable overflows. Hence, in the last step of our framework, we will rerouting those unassigned segments. Here is an example. There is a visible two-dimensional routing pattern in Figure A. If a conventional DP-based method is used as shown in Figure B, no matter which net is routed first, it must end up with one overflow. The overflow here is caused by the gap between 2D and 3D routing. In this layer assignment instance, our concurrent layer assignment will also cause an overflow, and thus, one segment of the red net is not assigned. For the red net, we will remove those redundant segments and vias as shown in Figure E, and perform 3D rerouting, and the result is shown in Figure F. The proposed concurrent layer assignment scheme has great ability to guide the 3D rerouting process, which is totally different from the conventional rip-up and rerouting after DP-based approach. Figure A shows a net with 6 wire segments, and 2 segments pass through congestion region with overflows, as illustrated in Figure B. As illustrated in Figure C, the rerouting of 2 separate segments may not effectively reduce overflow because it is very likely that their neighboring regions are still congested. In contrast, since our concurrent layer assignment scheme assigns the segments of a net from its pins, the unassigned segments of the net are connected as shown in Figure D. Thus, the illustrated in Figure E, the rerouting of the unassigned segment may find a less congestion path due to the larger solution space. Here comes to experimental result. We implemented our algorithm flow with the C++ programming language, and all experiments were performed on a 3.5 GHz Linux machine with 64 GB memory. We compare our algorithm with three major techniques which are commonly used in prior work. The first technique is dynamic assignment with via domain consideration. The second technique is the decompose large net into small nets to increase the solution space. The third technique is 3D rip-up and reroute. Here shows the experimental result compared with the DP-based approach with all techniques. Our algorithm averagely reduced the maximum overflow by 32%, the overflow tiles by 28%, and the runtime by 60%, with only 4% wire length overhead. Finally, here is our conclusions. In this paper, we present a concurrent layer assignment framework, which mitigates the net ordering problem that previous studies suffered from, and assigns wire segments of all nets layer by layer to minimize the total overflow. We propose a 3D demand prediction map. The prediction map calculates at least demand each tile of the current layer should be assigned. The prediction map can guide the wire segment assignment process to fully utilize the routing resource and minimize the overflows on the topmost layer. The experimental result shows the huge improvement over conventional DP-based approach with techniques commonly used in prior works. Thank you for listening.